So today my goal is to get everybody up to speed on problem 3, to make sure that we understand some of the issues, and we're getting into perhaps, unless somebody already has covered the set of all stuck-at faults by 10 test cases. If we haven't solved it already, then by the end of today at least we'll be ready to move full steam on it. So what I wanted to do for starters was to take a look at that simple half-add circuit as an example of a much smaller circuit than the big 400 gate one, and see if we can't get some insight into the large problem by studying a small one in some detail. Let me try to write that down again. So the half-add circuit had inputs x, y, and z, and we formed result 1, which was the exclusive OR of x and y. Called that A. And then we had the AND of x and y. I guess I didn't plan this too well. And call that B. And then we had the exclusive OR of A and Z. That's one of the outputs, U. And we have the AND of A and Z. It's getting worse. Okay. It's the AND. We call that C. And finally we had B or C, which is called V for OR, I guess. Okay, so that's V. No, that's not a very good diagram, but that's why I preferred to give it algebraically. In fact, of course, hardware people use all kinds of special symbols. I don't know what the various things for gates and so on. I don't think they have enough symbols for all the different Boolean functions, and anyway, exclusive OR looks pretty good that way. So so we also had the straight line description, which is like used in compilers, and gives you what they call a DAG, a directed acyclic graph, where we said that A is equal to x exclusive OR y, B is equal to x and y, C is equal to A and Z, and there was U, the outputs. U is equal to A exclusive OR Z, and B was B or C. Now this is the circuit that has 2 outputs and 3 inputs. And the idea is that if we are trying to add three 1-bit numbers together, then this gives us the 2 bits of their sum. So the units bit is going to be U, and the 2's bit will be V. So that's going to represent whether or not the sum x plus y plus z is 2 or more, is V, and then U is going to be x plus y plus z mod 2, the other thing. So this adds 3 binary numbers and gives us a 2-bit answer. Okay, now the question to ask on this is, let's try to make let's try to look at the stuck-at faults on it. There are 10 possible stuck-at faults. However, we don't consider the ones at the out. Let me see. I guess we do consider the ones at the output, yeah. But they're sort of obvious what would happen. I mean, if U is stuck at 0, in order to detect that fault, we would have to find some input which makes U equal to 1, and that's x plus y plus z is odd. We'll do that. Similarly, V. So let's take a look at A, which is one of the more interesting gates, and try to see what we would have to do in order to have A stuck at. Suppose A is stuck at 0. And just look at that problem first. So suppose A is stuck at 0, how would we catch that? What would be a test case that that detects A stuck at 0?
Either X or Y to be 1. No, you want them either X or Y to be 1, but not both of them.
Okay, so first of all, you want X. So first of all, you want X plus Y equals 1.
Oh, that's right.
Okay, is that going to be good enough to detect that A is stuck at 0?
Yeah.
No, there are two
you also want
necessary
it to-
conditions.
Yeah, you also
It's got to propagate through to a visible output.
It's got to propagate to a visible output.
If Z is 1, then it will change.
So if Z is 1, it will. Then you will have the wrong value.
Or 0, I mean, it doesn't matter.
Yeah. Okay. So it does. So in fact, this one does propagate. Since the exclusive OR always changes its state if one of its input is wrong, then in fact U will be wrong if A is wrong. All right. Now let's try B. Well, let's see. Okay, so A stuck at 1. I guess we could make a systematic chart. So how about this? A, and then we have stuck at 0, and stuck at 1, and we got A, B, C, U, and B. And the case is that A is stuck at 0 is one. Well, this is one. I guess we've actually characterized them all. Is that X exclusive OR with Y is 1. So I want to write a shorthand notation for that, and I think I can call it X bar Z. In other words, any input for which Y is equal to X bar, the complement of X, will detect A stuck at 0. What's the corresponding entry for A stuck at 1? Andy? XXZ. Because the same argument works. It's just that we got to have we got to have a value that makes A incorrect, and we also have to have values that makes the result visible in at least one output, but it is. So XXZ will do it. Okay. So B is the next one. So let's try B stuck at 0. And so there we want A and Y equal 1. We also want B to be visible.
That's given. That's normal. I mean, because X exclusive OR Y will be 0.
X exclusive OR Y will be 0.
So the input to C will be have at least 1 0.
Because X and Y must be 1.
Right.
Okay. So now we got X and X exclusive. So we got a 0 coming in here.
No, in C.
A 0 in C.
So that makes a 0 out.
So no matter what Z is.
Right.
Okay. Well, so here we're using backward and forward propagation of our argument. We said that since B is 1, then X and Y, its inputs must both be 1. Therefore, coming downward, this must be 0. Therefore, this must be 0. And therefore, it will propagate through the OR. So the examples for B stuck at 0 are 1, 1, Z. Okay. How about B stuck at 1? All right, so here we've got B is stuck at 1, and we want to get it through to our output B.
You need either XX0 or XX complement anything. think.
Oh, okay, so you've looked ahead. How did you give me the steps? Because we want a computer to be able to do this too.
Well, you want the other input to V to be...
Okay, so we want, in order to get through this over here,
you don't want the other input to be 0.
it's the only way that B comes to the output is through this way. So you see, in the case of the exclusive OR, if that wasn't a plus here, A was coming through, would have a chance to come through and affect V also, but we had it already detected at U, so we didn't need it. But at least one output has to be affected, but not every output. But B appears only in V, so the only way to get through the value of B, if C were 1, then it doesn't matter what B is. So we have to have a 0 at this point. So we also have to have A and Z is equal to 0. Okay, and now, so A was the exclusive OR of X and Y, and so
So if X and Y are both 0,
if X and Y are both 0,
then it doesn't matter what Z is.
if X and Y are both 0, then Z is then A is 0. But if X is 0 and Y is not 0, then Z has to be 0. So we had 0, 0, and anything. Then we had X bar, and 0. That's what those were the two cases. So here we had 0, 0, Z, or X bar 0. Everybody with me on that? I mean, don't be afraid to say no, because I don't want to lose people, but I don't want to go too slow either. So I got to have some feeling for tempo. I've been asking for volunteers for answers, but not volunteers for. I should pick on somebody at random and find out. Yes. Better. Okay, and then C is another one. Let's complete the table. Maybe we can do it in our heads. Let me take at random, like Mike. You're random, aren't you? Okay, C stuck at 0. How do we?
Okay, you're going to make C1, so
Mhm.
you'll need Z1, and you'll need 1 of X and Y.
Okay. Exactly 1 of X and Y.
Yeah, so you need X6 complement there.
That's in order to get a 0 out of
But
B.
that'll also give the 0 to V, which is what you need.
So we got XX bar, and now that makes C equal to 0.
Equal to 1.
Well, C is equal to 1, and therefore stuck at 0 ought to be detected provided that B is equal to 0,
And that's true.
which is indeed it's 0, because XX bar is 0. Okay. Right? Okay, Roger. C stuck at
next, right?
C stuck at 1. How can we do C stuck at 1?
Well, again, it has to reach the output. So you want X and Y. Let's see. You want B being 0.
Yeah. Okay. B is 0. That's this guy again.
And you want. Well, let's see. You want to make C 0, so you have to have either Z0 or X and Y equal. So
That looks like what we did here. Okay. X and Y unequal. Yeah. Z0 or X and Y equal to 0.
X and Y, the exclusive OR equal to 0. So
Yeah. Okay. I mean, it looks like the same two equations that we had for B stuck at 1.
It's exactly.
Isn't that right? So okay. So we ought to get the same answer. Okay, John?
This is
too easy.
Easy, yeah.
But let's write it down and complete the table. So just dictate.
So, for instance, U is okay.
Okay, suppose I know X and Y.
Then C should be
express it in terms of x.
Yeah. Because if x bar, then you want y. And
Could you do it in terms of two sets again? We have x bar 0.
Yeah, if you don't like this notation, although this notation wasn't quite right for stuck at 0. This gives the value of u x exclusive or y exclusive or x, it would be 0. And so this is for stuck at 1. So this would have been the correct. Putting a bar over is also exclusive or with 1. Okay, now you can consider the two cases that x equals y and x is unequal to y. So you have, for example, x bar, and then that makes 1, and so we need 0, or x 1. All right. Okay, what do we put here?
Right. 0. Or what? It's the opposite of that. Yeah. Okay. Sorry. Right.
Okay, let's let John tell us about v then, and then we'll have our table done and we'll see.
okay, it's the same.
Is that actually the detecting the C stuck at 1, you want,
For
I think I didn't get that backwards from D, actually.
Oh, really? For c stuck at 1, we want c to be 0.
So that X and Y have to be either equal or Z has to be 0.
That's what you have.
C has to be 0, and I wrote x, and that's a and z equals 0. So this is c equals 0. The other case was b equals 0 in order to get through the or.
Right, no, it's just that, I mean, you have, I think you want 0, 0, not Z, and then, or maybe you want to either have not Z or you want to have X equal to Y.
So in other words, our answer for b was also wrong. What you're saying?
Yes, no, the answer for B is okay.
Well, but the answer for b at 1 is the same as the answer for c at 1, isn't it? Because we said that for b stuck at 1, we needed b to be 0 and c to be 0. For c stuck at 1, we needed c to be 0 and b to be 0.
No, for C stuck at 1, we need A equal to 0 or C is equal to 0.
Why?
Because B doesn't feed into C.
But you have to get it to the output. So
So you have to get to the output.
B,
Oh, wait.
b feeds into the,
Oh, we're going to call it.
yeah. So it's always helpful to, questions of logic, it's always helpful to have pencil and paper handy. I think intuition somehow fails. This is the, you have all these problems about one tribe tells the truth and one tribe lies, random and so on. And the solution to this always seems to say, well, here you can check this out with pencil and paper, and in every case it works. But I don't know anybody who really intuits these solutions and sort of sees them happening. You can just check that they do exactly work. Now let's check this one again, because it might be wrong, since at least I claim that the two answers, the two lines up would be the same. We may not have the right answer. So if x and y are both 0, then z is arbitrary, because that will make b and c both 0. If x and y are not both 0, then one is 0 and the other isn't. So a is 1, and so z has to be 0, which is the second case here. So,
Well, I guess the other thing you can put in there is not X and then X, 0.
not x and x 0 is another thing we could add. However, I would probably rather call that not y and y. But so what? It's a free variable, and not x ranges over the same values as x. So what I mean by x in this notation is probably what's skewing you up. This means either 0 or 1. X bar. So this is a shorthand for two solutions. And the number of free variables that I put in here indicates the number of cases, and I think we've used, well, this comma is actually over disjoint sets the way we've got it. So here I found how many solutions for A stuck at 0, how many things?
Yeah, no,
4, X and Z independently. Here we've got 2 ways to do it, here only 2 ways to do it. Here we got 2 plus 2 is 4, here we got 2 plus 2 is 4. So the number of ways to do it is might disambiguous the thing. Okay, now what about V then? Now we want V to be, say, stuck at 0. So in order to get V stuck at 0, it's equivalent to saying that it's, I mean, for that to be a fault, it should be equal to 1. So what are the cases that make it equal to 1?
First, you can.
So we want V equals 1. And
B equals 0.
so, excuse me? And then we also have the condition that V gets to an output to be detected. However, that condition is no in this case.
It is equivalent to the two conditions that B is stuck at 1 or C is stuck at 1.
B is stuck at 1 or C is stuck at 1.
How? Stuck at 0.
Okay, so we have V equals 1.
Produces a 1.
It's just going to be the 2 out of 3.
It's 1, 1, 0, x bar 1 is the 2
Oh,
cases.
Oh, sorry, I was looking at the 1 condition.
Okay.
Stuck at 1.
So so B is equal to X and Y. So B equals X or Y, or C is A and Z equals 1.
It's easier if you just look at what V means.
It's easier to look at what V means. Yeah, but is that what the computer was going to do? Yeah. This is in fact easier. We look at what V means, and V means X plus Y plus Z greater than or equal to 2. It's a majority function. Threshold function, they call it in logic. Function that's true if and only if the number of ones in the input is greater than or equal to some bound. But we're trying to also imagine, as we solve this, that we were computers presented with a 400-gate circuit, and we want to extrapolate to imagine data structures and algorithms walking up and down and so on, as we're doing this exercise too. So I was being a little more mechanical in this. So we have two cases: either B is 1 or C is 1, or both. Although knowing what the answer is going to be is going to help us check it, but let's forget that while we derive the answer. Try to be mechanical. So suppose we take case 1, that B is 1, then that tells us what? Tells us
That X and Y are both.
X, yeah. So that's a 1, 1, Z is a solution. Okay? Now what's another solution?
X bar Z.
Excuse me?
X bar 1.
It's that A is 1 and Z is 1, which is X bar 1. Okay. And those turn out to be disjoint, in fact. Although, I mean, just because it turned out that the B or C cannot both be true simultaneously. If we had another gate in the circuit that was calculating B and C, it would be very hard to detect that it was stuck at 0, because it would always be that wouldn't be an error, because it always has to be 0. B and C, if that were in this circuit somewhere else. It's possible to design circuits that have so that all combinations of the input will in fact produce outputs of 0 or outputs of 1. And in which case it would be very hard to detect a fault on that gate, since the gate is redundant, unless the gate is stuck at the wrong thing. Okay.
Well, so isn't it kind of a problem to simplify the circuit first? Because you get rid of those gates which could be stuck at the opposite.
There are some simplifications that we know can be made without looking at the inputs. For example, if a gate, in the problem that you have, there's a simplification that says if one of the inputs is 0, then you know the output, and so you don't put the gate in the circuit at all. If you have an AND gate and one of the inputs is 0, then the output is 0. If you have an OR gate, one of the inputs is 0, the output is the same as the input, and we just hardwire. We just imagine a short circuit. We don't put a gate in, and so it never goes into the data structure. But somehow we keep track of this as we're building the data structure. Are you with me? The other kind of simplification is a gate that's never actually used in any of the outputs. I think there are about a dozen of those in this circuit. That they're actually, the gates are explicitly specified in that module, but they don't ever appear in any output.
I see. So the ones that have an AND gate with a 0 input is in the specification you give, but it's not really in the circuit.
It's not really in the circuit.
Okay.
Yeah, it disappears and it drops the circuit down by a factor of 2 or 3, I think. I forget what the numbers were, that kind of simplification is done a priori. However, suppose somebody also had another circuit in this case, and also put an AND gate in here between B and C. Suppose there was a B and C and another output W. Suppose that we had added this to a triple adder, some kind of a thing. It's better than a half adder. We're going to get a patent on it. So we have this new gadget here, W equals B and C. And now I say, now let's make a test case which is going to check for W stuck at 0. So in that case, we would need to find a case where W is equal to 1, and it never is equal to 1. So this would be a fault that we couldn't test for.
I think there are actually gates like that in the circuit you gave us.
You think that there are some gates that are known to have a constant output in the circuit we gave? Okay. Well, let's get to that later, because that will be important news as far as.
Well, wait, but if a gate is always going to give the same value, then again it's redundant and shouldn't be part of the circuit.
That's right. So we could eliminate it from the circuit.
There are gates like that which don't have 0.
I did the 2x2, the 3x3 one, and there was a gate like that. I can't remember.
Okay, in the 3x3 case. Yeah, well, let's take a look at that later. Good point, Mike. So anyway, at this point, B and C cannot both be true, and we have to face up to that fact that this might happen in the circuit. And the reason I thought of that in this problem is that, well, I had two cases, one or the other, and if I were to try to look for after I'd solved the first case, to solve the second one, I could assume that B was 0. I could take, instead of this or, I could say C is this and B equals 0. Because I've already considered the case B equals 1. And so then this would be the exclusive or. I mean, it would be either this case or this case, but not both. But in this case, when C is 1, B is equal to 0. So this is, in this particular circuit, the two things are mutually exclusive. So these were the cases that B is equal to 1, and it really means that we have at least two of the x's and y's, and two of x, y, and z are on. Either x and y are both on, or z is on, and one of the other two. Okay, then what's the other case then? V stuck at 1. That's the last thing in our table. V stuck at 1, let's figure it out. This means that this has to be 0. Okay. Now let's go to Amy.
See, that would mean that we need x and y equal to 0.
Yeah, because B and C both have to be 0.
X exclusive or y, and z equals 0 also. So you could have x and x naught and 0, I guess.
Okay, so so you're saying x naught 0.
Or if both x and y are 0, then z could be anything.
Okay, 0, 0, z. In fact, that's, let me just write it the other way because that's a familiar entry here. Okay. It's the same. It turns out that here we had 3 different ways to get to the same. These inputs detect the same Stuckett fault. Okay. Now this is a complete table showing exactly all the cases of for each fault. Now in our problem we don't need a complete table. It's not. It might be. It might take an hour to, or no, it might take a long time to list all the inputs that produce a certain Stuckett fault. And a chart like this, a list like this might get very long on a much larger circuit. And we could always list them out if we need to. But only one of these is good enough. We just have to cover each fault. We don't have to find all ways of doing it. We just have to find one way of doing each one. And if we decide, for example, that we're going to look at this one and forget about that one, we might not get the minimum cover of all 10 Stuckett faults, but we might have a good chance because they're usually on a minimum cover problem. There's many ways to get the same minimum, and so just take one that looks pretty good. Might be good enough. On the other hand, if we restricted ourselves to just taking the first case that has a Stuckett fault, suppose we just choose one, like x equals 0 and z equals 1 or something in that case. Then we're only finding that. Then we're saying we probably need a lot of test cases. So it's desirable to know as many of these things that cause the faults as you can conveniently, but still it's not necessary to know all of them if that's going to take you too much time. There's a trade-off between exhaustion and expediency. The problem will be, I think the total problem of finding the absolute minimum cover would be expensive enough that I wouldn't want to pay the bill. I wouldn't want to, increase the national debt by asking for funding for all the computer time that would be taken to find the exact minimum. Maybe someone will figure out a way to make me wrong on this. So my point is that here we have complete information, but any subset of this, any non-empty subset of these entries could also lead to a way of covering all the faults. And you want to take the largest convenient subset, probably. Now let's see. Now, Mike, you said in the case of say multiplying 3-bit by 3-bit, you found a gate that was.
It was either the 2x2 or the 3x3 that I was looking at. And there was a gate in there that was 0.
Can you describe which gate it is?
It was one of the. It was the 36 gate, right? It was one of the gates that produced one of the top 2 bits, and it was an OR of 2 things, and one of the things was only 0, I think.
Okay, so you found that in the final phase of let me see.
Soil T-shirt.
But you didn't identify it further. Okay, so the last actually we have in our final ad.
Draw the 2x2 case and I'll find out.
There's a 4x. We're adding two numbers together, I don't know what the right notation is for it. So let me use what I know is the wrong notation, and then it won't be mistaken for the right one. This is we have a parallel adder for two things, and the first thing we do is in this parallel adder is that these are going to add together the results of the different partial products, and we've reduced it by changing 3 to 2, 3 to 2, 3 to 2 until finally only 2 are left, and this is going to be the final coup de grace. The end of the multiplication will be the sum of these two numbers, and we did a parallel add on these, and let's see what the formulas were. Z3, Z2, Z1, Z0 was, I think, was Z sub k was equal to xk plus yk, and then we had let's do it the way it really looks on a 2-bit case.
Mike, how did you know the input was 0?
Sorry?
How did you know the other input was all 0? What was it coming out of?
I was just looking at the circuit. It was it was something like AND of an AND of 2 bits and XOR of 2 bits and then AND those two together or something like that. I can't remember exactly what it was anymore.
Okay, well, let's just take a look at the details of this part of the circuit, because I think it'll be useful. So then we had also, there was another thing called, let's say, I'm sorry about the notation here. WK was equal to XK and YK. And then what we did was we called the routine C1 of 0 and B W0, W1, W2 with 0, Z1, Z0, Z1, Z2. I think that's what it is. And then we call C, and this computes this goes to, say, C6, C7, C6, C5, C4. I'll have to find a better notation for this. Or we could put it into the notes we had last week if I could remember exactly what the notation was last week. Now this, then we did a C2 on this guy, on C7 through C0. Oops, I numbered it wrong. 0, 1, 2, 3. Okay, so all this backwards. And then you do a C2 of this, and that goes to the output. That goes to D0 through D7. And then finally, the final circuit was to add this guy so you're doing 2 bits by 2 bits. Is that right? Well, let's take 2 by 2 because it's going to be I won't get too bogged down if we do 2 by 2. That 2 by 2 gives us 4, and we get these. Oh, okay. Well, that might help because wait. Let me see what did I do though? At the end, I add 15 bits. Okay, so 15 is now 4. So this is it. I just add the B3, the FI 0. So it looks like I take D3, D2, D1, D0, and this is plus this. And so we get the final answer was going to be the exclusive OR of these guys. So what we actually computed, if you remember from last time, we had the sums of the exclusive OR, sums mod 2 of the extra, and then we had to exclusive OR on carry digits that came from before. And so the so D3 is going to represent the condition. There's a carry from the right of this point. And D2 is going to represent the similar thing. Now, is it possible that D3 will always be 0? Or that...
I mean,
Higher
in a
result
way,
bit is always 0, isn't it?
Yeah.
Is that the gate? That's not the gate you're talking about.
no,
Okay. But in calculating D3, let's see. Let's take a look at the what is this? What does this one do? D0.
doesn't it mean that your simplification is wrong if you get those gates like that, as we discussed earlier?
My simplification is wrong. Yeah. So, what do you mean now?
That if the first stage of your program simplifies the circuit properly, it shouldn't get any gates because outputs always are the same value. It should simplify those.
It may be hard to catch them, but
It may be hard to catch them, but if you do catch them all and simplify it, then you get rid of those. Is that
correct that if we catch all the zeros, then we don't get any other simplifications? We have an example. We have an example here.
we're just catching
So
zeros.
there are other situations things like if an exclusive OR gate should happen to have both of its inputs connected to the same place.
Yeah, or if an AND gate or if an OR gate has an X and an X invert and an X naught coming into it.
Right. Then we know
But it's
that its output is
that's a very hard problem to consider.
No, it's not really. I mean, that's
Well, those cases aren't, but I mean, there are some which are.
yeah. So I believe there are situations
well, it might be.
that where this could happen, namely that no matter you exhaust all the possibilities. For example, let's suppose we're multiplying numbers. Maybe this can't happen in number theory, but this would be an interesting way to prove that it can't happen. Suppose we look at something in our final product here, and the only way to get a certain gate to come out, a certain condition to occur, is if the final number after the addition is equal to all ones, for example. But if that number, all ones, is a prime, then it would have to, then what x and y, when you multiply x times y, would come out to all ones, since it's a prime. So there won't be, so every final answer that we come through here is going to be something that can be written as a product of two-digit numbers. So there are certain cases that are excluded by number theory. One of them may be 1, but a two-digit number is small. So there are lots of there's number theory somehow is in test for primality is somehow being encoded in these AND and OR gates here. Not primality, but test for not having a large prime factor, a prime factor greater than a certain number of bits. So this is why it might be possible that some of these things don't occur. But I wanted to look in detail at the carry propagator circuit because it mightn't be obvious that the thing is always 0 if we look at the carry propagator circuit. So I'm trying to go back out of my notation to this one. You have if you can, meanwhile, you got it written down.
This is the 2-bit case. I can't find the example as anyhow, so I'm just thinking about the 3-bit one. But this has another example of 2 gates that always produce the same result. G5 is all of the bits ANDed together.
This is the entire circuit?
This is the 2-bit multiplier, yeah.
That's simplified.
That's after simplifying out the ones that have only 0 inputs.
Okay.
And also don't contribute to the output.
Yeah.
So you're saying this is the entire circuit for the 2x2 case?
Yeah.
Okay, well, I might as well draw that down instead of getting bogged down in this one. Okay, Mike wrote it this way.
That's Andy's diagram, actually.
It's Andy's diagram. Okay, this is Andy Tucker? Andy Golden.
It's upside down.
We have,
It's upside down.
it's upside down.
It's the longest
Everyone else is
line of
upside
argument.
down.
Okay, well, let me do this one, but it looks a lot more, this one looks a lot more professional, so I'll do this one. Boy, okay, so here we got this guy, and we got this guy coming over here. This is great, isn't it, to have all these? Oh boy. No. Then there is AND gate here. So this is G0, which is, this will be stand for an AND gate. And G1, G2, G3. And we know about those. We want to take I0 and it on to I2 and I3. And that gives us G0 and G2. And similarly the other guy. Well, maybe it must be, this must be the Y. Okay. Then this is our final output, O0. This one, an exclusive OR gate, G4, it's known as circle plus. That one with this. And then there's a G5, which is an AND gate corresponding. Usually exclusive ORs have their corresponding ANDs next to them. And so that's this, put there. And then G3 into G6 and so to G5. Oops. On the G6 as an AND gate, is that right? And then we also took this into an exclusive OR gate here. I'm almost done, but gang. G9. This is O3. This is O2, and this is O1. So the claim is, in that case, that one of these gates has a constant value.
No, in
this was after this.
This doesn't have a, the G6 and G5 always have the same output. There's an example.
G6 and G5 always have the same output. So
because G5 is I0 and I1 and I2 and I3.
Right.
G5 is equal to I.
It's I0 and I1 and I2 and
It's
I3.
the AND of an AND, and these are I0. This is I0 and I3. This one is I1 and I2. Okay, so G5 is the AND of everything. It says that G5 will be 1 if and only if they're all equal to 1. Yeah.
And so then G6 you're ending some of them back in again, which isn't going to change anything.
It's just redundant stuff.
Oh, okay.
So you can actually just get rid of G6.
So you're saying that G6 is equal, which is G5 and G3, but I don't have any complementing in this circuit, so 1's always stay 1. So that G6 will have to therefore always come out to be the same as G5. So it's a redundant gate in that sense. Now so it doesn't have.
However, though, you could detect the stuck-up fault.
Yeah.
Yeah, but supposing you had something going from there into an XOR.
Which is
from the two, between the two of them.
Right. So now, if we had G5 XOR G6, we would know that the XOR is always equal to 0 because they're always equal.
But that is the problem, finding out that they are equal.
Yes, I don't think it's something that can be determined really, other than trying all 2 to the 16th inputs in the 8-bit case.
Well, or by some kind of a back and forth situation. Okay. So there is a way. Okay.
It says like a
But yeah, I thought that was going to be easy.
I don't know which is smaller though.
What you say, Rich?
That's just the problem. It's the trade-off between trying all inputs versus doing the satisfiability problem, I guess, right?
There are many ways to study problems that are exponentially hard, and it depends on other constraints as to which one we want to try at a particular time. We might wind up, if we have 6 teams, 6 different approaches, and not always clear which one is going to be faster, depending on for example, Pascal doesn't have a good way to do full word exclusive OR of numbers, but if you're writing in C, you can do that. So you could be testing 32 cases of a circuit, doing full word Boolean operations in C by just by setting up your X, Y, and Z to be 32-bit numbers, but different ones. Run it through the circuit. You get 32-bit output, which gives you 32 examples of what happens. And so if this. On the other hand, if you're using another language, that might not be a good way to, you might be handicapped by not being able to do full word Boolean operations that are in your hardware. I wanted to see if I can't figure out okay, well, I think I'll just defer that. So there's a possibility, though, that somewhere in the last stages of the addition, that there will be a gate that's known, whose output is known to be 0. It can never be true that a gate is known to be 1 in this case, because we don't have any ways to turn 0 into 1. If all the inputs are 0, everything is going to be 0. We don't have any inverter. It's only ANDs. It's only ANDs, ORs, and exclusive ORs in this problem. Now, the next thing I wanted to discuss this morning is, suppose you have a set, and suppose we take the dual problem. Instead of starting with a stuck-at fault and saying what inputs produce the stuck-at faults, let's start with an input and say what stuck-at faults does this input detect. So let's go back and see if we can solve a corresponding problem. So now, so my inputs, for example, 0, 0, 0, which faults would that detect? So now, so my inputs, for example, 0, 0, 0, which faults would that detect? And so here we have A0.
This table already?
What?
Are we pretending we have this table already or not?
Well, what do you think we should do? B0, B1, C0, C1, B0, B1, B0, B1. Let's just, so we have 8 possible inputs, but let's suppose that we take one of these at random and figure out which stuck-at faults it has. Let's pretend we don't have this chart to look at, but that we're taking this as a separate kind of a subroutine. So somebody has given us an input, and we would like to know which stuck-at faults we pick up. So let's forget we did the other table and say that we have x equals 0, y equals 1, z equals 1. That means then that A equals x exclusive OR y is equal to 1, B is x and y is 0, C is A and Z is 1. U is equal to A plus V, which is 0. V is finally B or C, which is 1. Okay, so which stuck-at faults do we detect?
For start, you can only detect ones which are the opposite of those gate values.
Okay, so first of all, it's going to be A0 would be
We might detect
A stuck at 0. We might detect B stuck at 1, C stuck at 0, U stuck at 1, or Z stuck at 0. We might detect, but there's another condition that it affects the output also.
Well, for U and V, that's obvious.
For U and V, it's true. So, and what about for the other ones? Is there a fairly easy way to understand in a circuit whether or not, if you know the values of the other variables, if you know whether or not you get through to the output?
Well, since C is 1, you're not going to see B.
Right.
Yeah.
Since C is 1, you're not going to see B because it obliterates B. So
Likewise, B is 0, so you are going to see C.
Correct.
Yeah, well, in general, the only ways to mask it are ORing with a 1 or ANDing with a 0.
Or going through it.
wait a minute. Yeah. Okay, let's do that slow motion. ORing with a 1 will mask it. ANDing with a 0 will mask it. And then Arif has a
No, I was talking about the
Well, you can
what
actually
will allow things to pass.
exclusive OR
with
Will
yourself.
always pass
exclusive
through.
ORing with yourself will.
Or
That's a more general problem as soon as you
Well,
start.
yeah. If you allow things to feed back like that, then you also have to worry about ANDing with the complement and XORing with yourself and stuff.
So yeah, it's
Actually, there is no feedback in these.
but that you could bridge.
it's possible to have, for example, a circuit that's
It's not cyclic, but
okay. You have a flaky part of your circuit, and its output comes out here, and it's supposed to be 0, but it's really comes out 1. And now here you'll use that in 2 places. Maybe you exclusive OR it here with somebody, and you exclusive OR here with somebody else. Now, if you come back here and exclusive OR these together again, then this one is not affected by the wrong output of this guy. For example, and there are other cases like that. Now, so simply having a clear path of exclusive ORs to the output is not sufficient to get to the output. If this were an AND, something like that, okay. But it's just having just the existence of a path of exclusive ORs from a gate to the output doesn't mean that you always be able to pick up the gate. Okay. So suppose that we try. I like this problem because you get to try the paradigms of programming that the professors teach you, and say, try to imagine, for example, finding some subproblem, some invariance that you could solve. For example, maybe with each gate we could consider associated with it the set of all stuck-at faults that we could obtain if we had only the circuit up to that gate. You see what I mean? I start out with a circuit that's trivial, and at X I say that the only stuck-at faults that I don't know exactly how I started. After A, then I suppose I have a circuit that has only gate A in it, and then I try to evaluate a function at A, saying this is the set of all stuck-at faults in the circuit that I could do. Then I try to consider the operation if I have the exclusive OR if I add an exclusive OR to the network, and I already know the set of stuck-at faults that are produced at the two sons of that exclusive OR, then what's the set of stuck-at faults for the new gate, and sort of propagate downwards that way. I'm not going to solve the problem now. I'm just pointing out that then you might want to look at that. In this particular case, though, let's finish this problem. Let's see.
But then you also have to go backwards once you get.
So what I'm saying is it possible to go? Suppose that somebody gives inputs X, Y, Z. Would there be a forward algorithm or bottom up algorithm or whatever you want to call it that systematically evaluates something, and then when it gets to the end, the list of stuck-at faults on U and on V will be the stuck-at faults for the whole thing. But going forward, not going backward. Only. I think there might be a forward-only algorithm.
Well, you can just simultaneously evaluate the circuit with and without the stuck-at fault.
Yeah. In other words, imagine that you had both C, for example, both A and A prime, and then A prime is used in all the outputs of A, or A bar or something, and I guess you just change the circuit so that after that point you use A prime instead. Okay. Let's finish this problem anyway first. What about this? Is A stuck at 0? Is that actually detected by this particular input?
Yeah.
It is, because we know it doesn't depend on Z. It comes through to change U. Okay. And C stuck at 0. C stuck at 0 would get through to V because B is no. Because B is 0, so this one doesn't come through either.
Yeah, that's right, because you have an OR gate.
Oh, it's an OR gate, excuse me. Okay. Now, I consider it might be a valuable thing to work out a fast algorithm for figuring out the solution to this problem. I'm not sure it is or not, but my intuition says it's interesting to start out with a given input and to compute the set of all stuck-at faults that it will do it by some reasonably fast calculation that goes from the bottom to the top. There's a top-down approach also to the stuck-at faults, and this. Suppose, for example, that I wanted to say, does V depend on A? I want to show this quickly because we're running out of time. But V is a function of the inputs X, Y, and Z, and we can take any Boolean function and write it in various canonical forms. You can write a Boolean function as in disjunctive normal form, for example, and so on. But since we got a lot of exclusive ORs, I think the form that writes it as exclusive ORs and gates and forgets and gets rid of all the OR gates is a nice canonical form. This is the same as polynomial modulo 2. So if you have only exclusive OR and times, this is the same as working in modulo 2 arithmetic with zeros and ones. And so x times x and y is xy, x exclusive OR y is x plus y, and x or y is x plus y plus xy. And so we can think of this as a polynomial. Any of the gates, the result of any gate in a circuit is a polynomial in the inputs x, y, z, where we just take the value of the polynomial modulo 2. And you can, and if we look at this thing, if we imagine that a particular gate in the circuit was an input, or I'm really considering it as A prime, And I imagine that this connects to V by using A prime instead of A on the output lines. I never use A as an output, but I just have all the inputs coming through, except wherever they go through A, I stop the path. Well, this would be A x, y, z times, let's say, f of x, y, z plus g of x, y, z, where I've replaced the polynomial in x, y, z by a polynomial in A, x, y, and z. A is the, actually, this is, I guess I should leave out the A. This should be A is the result of gate A, and it's been combined with other polynomials. So f and g are polynomials, but A is the coefficient. But A, these are the terms that have an A in them, and these are the terms that don't. Now the condition that A is recognizable in the output is then what? What's the condition that if I let's actually do the calculation so that you see what I'm getting at here. So V is equal to B or C. So that's B. B plus is exclusive or addition mod 2. So this is B plus C plus BC. B is equal to XY. Oh well, let me do it. So this is XY plus C plus XYC, and C is equal to AZ. So this is XY plus AZ plus XYAZ. Now if we take any output and keep expanding until we get to inputs, but I never expand A because A is the gate I'm testing to see whether it's stuck or not, then I can write this as A. I can factor out Z plus XYZ plus XY, the part that are multiplied by A and the part that is not multiplied by A. And this is just polynomial arithmetic, which we know is legitimate to work with polynomials this way, although it happens to also apply to Boolean functions. Now, this is what I call F, and this is what I call G. Any function, any output, and any gate, I can decompose as that gate times some polynomial in the inputs plus another term. Right. So Neil.
Oh, so you want the function f to have value 1. So
Yeah. F equals 1 is sufficient to say that this gate does affect the output. That's the necessary and sufficient condition. And I think it's a nice algebraic condition. That's why I wanted to get it, bring it up today. So if f is 0, then you know, as a function of the inputs x, y, and z. If f is 0, this is the case that A is not getting through the output at all. But if f is 1, A is definitely getting to the output because changing A from 1 to 0 is going to complement the value of the output. And so in order to have A as a stuck at 0 fault, it's necessary and sufficient to have f equals 1 and A equals 1. And for A stuck at 1, it's f equals 1 and A equals 0. Those are the conditions for a. I think those are probably the nicest algebraic conditions for stuck at fault.
However, for 400 gates, you get a pretty big expression there.
Yeah.
That's right. So symbolic polynomial multiplication is not the answer here, but formally it gives you a necessary and sufficient condition that you can use to derive algorithms. But I'm not recommending multiplying and getting terms with 2 to the. I mean, there's 2 to the 400th possible monomials here. That we then add together, or add in or not. So this isn't going to. Yeah, these expressions will get large, but the derivation, however, gives us a theory on which to base other methods. Okay.
And even if we could find the expression, unless it was in some nice canonical form, it might be rather difficult to derive the input condition which would lead to all the input conditions which would lead to it becoming 1.
All the input conditions that would lead to it becoming 1, yeah. But on the other hand, well, let's take a look at, suppose you have a large circuit, and it turns out that for 200 of the gates, F is trivial. For example, suppose you consider a special case of F consisting of 0 or 1 terms. Okay? It might turn out that 90% of your gates have that condition. In this particular case, we noticed that, for example, that A always got through the output because, output U, because its coefficient had in other words, this Z here. If I took U is equal to A exclusive OR Z, which is just A plus Z. So the coefficient is 1. So it's and if the coefficient is equal to an AND of any number of terms, 0 or more terms, then it's a pretty simple case. So you might be able to use this algebra for a great vast majority of the thing. And then you have then use a more complex method for another one. With this, yeah. So anyway, thinking of worst case is not always the right way to solve a NP-complete problem, because then you're worried about the things that might not even arise in your particular problem. I don't want to minimize the importance of NP completeness, but I do want to say that almost every problem that's ever been solved, there are things that are worse than NP complete. Those are unsolvable problems that there is no algorithm for at all. But I venture to say that almost every problem that you've ever solved is a special case of some unsolvable problem. And the fact that in calculus, for example, to test whether or not a function, the limit of a function of n is 0 as n goes to infinity is an algorithmically unsolvable problem. But that hasn't stopped us from doing a lot of calculus on a lot of functions that we could actually evaluate that limit. Okay, now I hope this has helped some to get your mind thinking about problem 3. The last thing, how about teams? Has everybody got teams now for this one? And raise your hand if you're not yet a member of a team for the problem 3, because we'll pair those people together. Okay, you're now a member of a team for problem 3, and so we have all our teams for problem 3. So that's it for today, and Thursday is our big field trip. Okay, further details about this.